Hey everyone, welcome back to my channel. So far we've covered one interview question from one data structure. Like we talked about 2D arrays, we talked about linked lists and binary trees. I'll be putting links to those videos in the description below. You can go and refer to them. This is maybe the last video to that series for right now. Today we're targeting the graph data structure. And the problem that we're targeting is we have to detect if a given graph has a cycle in it or not. Let's spend a few minutes to revise what a graph is, what is a cycle in a graph. Then we'll write the code to detect a cyclic graph. Let's get started. A graph is a non-linear data structure that consists of vertices and edges. So each node in a graph is called a vertex that can have some data. And the connection between those two nodes is called an edge. Like here, these arrows are saying 2 and 4 are two different vertices. And then the edge connecting 1 to 3, 3 to 5, 2 to 3 are called edges. A graph is an umbrella data structure. What we mean by that is any valid tree that we see is also a valid graph. Similarly, if we have three nodes A, B, and C that are linked to each other, such that A is connected to B and B is connected to C, we know it's a linked list, but we can also say it is a valid graph. So any linked list or any tree is a valid graph, but the reverse may not be true. Every graph may not be a tree. So it has to satisfy the conditions of a tree to be called a tree. Graph has many real life usages. Like we can use it to represent any network. It can be the network of computers, or it can be a network of roads. So when we see Google Maps, all the routes that we see on Google Maps are actually calculated with the help of graphs. We have different types of graphs. The first one that we're going to talk about is an undirected and directed graph. In an undirected graph, um, one edge simply connects two nodes. For example, here A and B are just connected with each other. Similarly, A and C are just connected with each other. In case of a directed graph, one edge actually points the direction of connection. Like here we can see A is connected to B, but B is not connected to A. So the direction is also there. Then the next type that we have is an acyclic or a cyclic graph. A graph is called acyclic when I'm traversing a graph, say I start from A, I cannot come back to this node again. Whereas in a cyclic graph, if I start from A, yes, I cannot come back to A. But if I start from B, I can go to C, D, E, and then I can come back to B. So whenever there's a closed loop in a graph, that's called a cycle in a graph, and it's called a cyclic graph. Then the next category that we have is weighted and unweighted graph. In an unweighted graph, the edges are simply connecting the nodes with no other value. But in case of a weighted graph, each edge has a weight associated with it. And that weight can denote multiple things. It can be the distance between the two nodes, or maybe the cost required to go from one node to another node. So the path that we may choose to traverse a graph will differ based on if it's a weighted graph or an unweighted graph. For a weighted graph, we generally try to go for the minimum weight. Like if I have to go from A to E, I have two routes. I can go A, B, C, or I can go A, B, E, or I can go A, C, E. There's also one more route. I can go A, then B, then C, then E. But the most efficient route here is I go from ACE, because then the total weight will be 30. In case of ABE, the total weight will be 50, which is more than 30. So we try to optimize the weight. But in case of an unweighted graph, it won't make any difference. I just have to reach from A to E. I can either go ACE or go ABE, that won't make any difference. Now the next thing that I want to talk about is how we represent these graphs. Say I have this graph where we have A, B, C, D nodes. A is connected to B and C, B is connected to A, C and D, C is connected to A, B, and D is connected to only B. The first representation that we can have is called the edge list representation. In an edge list, we simply write, it's a 2D array in which we simply write the edges. Like the first edge that I have is from A to B. That's edge number 1. Then there's one more edge from B to D, then B to C, C to A, and there are just 4 edges. 1, 2, 3, 4. So in that 2D array, I'll have 4 elements, which will be the edges of that graph. Other than edges, the next representation is called an adjacency list. In an adjacency list, we simply write down all the adjacent nodes, all the adjacent vertices of any given vertex. So here we have A, B, C, D. If I talk about A, then the vertices that are adjacent to A are B and C. The vertices that are adjacent to B are A, C, and D. The vertices that are adjacent to C are A and B, and the only vertex that's adjacent to D is B. So if I know this, I can construct the graph. So this is one more way of representing the graph. The next way to represent a graph is called an adjacency matrix. So it's again a 2D matrix in which we write 0 and 1, and that marks if the nodes are connected or not. So I have A, B, C, D in a 2D matrix. So we know A is connected to B and C. So here, when I'm populating my 2D matrix, I'll put 1 and 1 only for B, C. The other values will be 0. Similarly, B is connected to A, C, D. So A will be 1, B will be 0, C 1, D 1. And in a similar fashion, I'll populate the whole matrix. And then with those 0, 1 values, I'll be able to figure out what the graph is. So we talked about different types of graphs, how we represent them. Now the next thing that we want to talk about is the algorithm with which we can detect if a graph has a cycle or not. Now we'll talk about how to detect a cycle in a graph. And the approach that we'll be taking is called a depth first search. The reason it's called depth first is we'll pick any vertex, then we'll try to look at all its connected nodes. Then we'll visit those connected nodes. If they have any other connected node, we'll visit those nodes too, and we'll keep going level by level into the depth of that graph. So it's called a depth first search. The end condition, in simple words, is going to be if I've started from any point and I'm traversing my graph, if I can come back to that point again during the traversal, that means it's a cycle. And that will end our algorithm saying that a cycle has been found. For example, here, if I go from A to B, then B to C, from C, if I can come back to A, and I started from A itself, A is already visited, so it's a cycle. But let's see how we can define that in a series of steps that we can feed to a program. So say I start from A, and I mark A as visited. Then I look for neighbors of A. We have B and C as neighbors. So A is visited. Now from A, I'll go to B. Then I'll look at neighbors of B. We have A, C, and D. If any neighbor is already visited, that means a cycle is there. So here we can see A is already visited. Does that mean we have found a cycle? So let's have a look. If we have A and B that are connected to each other. So if I'm going from A to B, and then I can come back from B to A also because it's an undirected graph, But is this a cycle? No, it's not a cycle. If I'm going back to the node from which I just came to the present node, then we will have to ignore that. And in this case, we'll be calling it a parent node. So if I'm landing at B from A, then A becomes the parent and A is not a neighbor, but it's a parent. If B is connected to any other node, say C, then C is the only neighbor, but A is not a neighbor. A is a parent. We'll be ignoring that. Okay. So let's do it one more time. We start from A, we mark it as visited, then we have B, C as neighbors. So we go to B, but when we go to B, we mark A as a parent. Okay, so it's a parent. Now when we are looking at neighbors of B, A can be ignored and we'll only look at C and D. Are they visited? No, they're not yet visited. So we'll mark B as visited here. Now we can go to any of the neighbor. Let's say we go to C. So A is visited, B is visited. Now when we're going to C from B, in that case, the parent will be B. And for C, there are two neighbors, B and A, but B can be ignored because it's a parent. So A is a neighbor for C. We'll mark C as visited. And now we check that A has already been visited. So that is our end condition. If we have landed at a graph, at a vertex that's already visited, that means we have detected a cycle. And we can very clearly see it here that ABC is a cycle. In case, let's say if this node wasn't there, this edge wasn't there, we had a graph like this, then we would have visited C. And since C does not have any neighbors, we'll just continue. B had one more neighbor, D. So B is visited, A is visited. This link, let's say it's not there. C got visited. Then we'll come to D. And when we're coming to D from B, then B is the parent. So we'll mark D as visited. We'll look for its neighbors. This is one neighbor, but it's a parent. It has no other neighbors. And now at this point, all my nodes has been visited. So when all the nodes has been visited, that's when we can say we have completed our traversal and we have not found any cycles. But in case we detect any cycle in between, then we can say it's a cyclic graph. Okay, it is time we coded our algorithm. I'm again going to write the code in JavaScript. So let me go ahead and create a class that is going to store our graph. So say we have a class graph, and we can store the graph in multiple ways. We can go with adjacency matrix or adjacency list or a edge list. Let's say we're going with adjacency list for this implementation. So I'll just create a constructor in which I'll initialize the adjacency list as a blank object. Now we're calling it list, but we're still using an object to store the information because the kind of entries that I'll have in this object will be in this format. So for each object, I'll have the node, like A is one node. Then we'll have connections, which will be an array of all the nodes that A is connected to. Then we'll have a Boolean visited, which can be true or false based on whether we have visited the node or not. So A can be connected to B and C. This is how we'll be storing our graph as an adjacency list. So the other functions that we'll need are, we have the constructor here. We need a function to add a vertex. We need a function to add edge. And edge is between two vertices, so it will take two vertices as parameter. And the implementation for these functions can be simply, if I'm adding a new vertex, then to my adjacency list, I'll add that as a key, So if A comes here as a parameter, then A will get added here, just how we have it here. And that will be an object in which we have connections, which is a blank array, initialized to blank array. Then a boolean visited, which is again initialized to false. When we're adding a vertex, it's not visited. Let's add vertex. For add edge, when we're adding an edge, we need two vertices, and we just have to make the connection. So to a already existing vertex, we'll add one item to its connection. So we'll go to the adjacency list and pick the vertex 1. Then to its connections, we'll push vertex 2. And since this is a undirected graph, if vertex 1 is connected to vertex 2, if A is connected to B, that means B is also connected to A. So I'll just copy this and do the same for vertex 2, add connection to vertex 1. If we are adding A is connected to B, then B is also connected to A. That's how you add an edge. These are the two helper functions that we'll be needing. Now comes our main function, which is to detect a cycle. Now, when we're detecting a cycle, we have to iterate on each node, on each vertex. Vertex and node can be used interchangeably here. So we have to iterate on each vertex. And for that, I can say let vertices equals to object.keys this dot adjacency list. So if my adjacency list has entries like these, so A is connected to B, B is connected to A, if we have added A and B. And when I'll do object.keys, I will get A and B, which is the list of the vertices in the graph. So once we have the vertices, I can just write a simple for loop to iterate on each vertex. And then for each vertex, I'll do a DFS to detect a cycle. And the reason we don't pick the initial vertex and just start with it, the reason we have to loop on each vertex is we might have a scenario where we have a disconnected graph where A, B, C can be connected to each other, but then we can have D which is independent. Something that looks like this. So A, B, C are there, but D is independent. So we'll have to iterate on each vertex because maybe the subgraph which is starting from D can have a cycle in it. So when we're iterating on each vertex, we say one vertex equals to, we'll pick the item from our adjacency list, which will be vertices index position. Actually, let's do it like this. So we have a vertex, which is simply A, B, C, our character value. Then we can have a vertex node, which is actually the object which is storing the connections and visited flag. So vertex node will get it from the adjacency list and we'll get the vertex key. Okay. Now we can say if our vertex node is not visited, if the vertex node is not visited, we can check for DFS. So let's say DFS for cycle. And if we run through the whole loop and this detect cycle will return a boolean, either true or false. So I'll just return false if the complete vertices have been traversed and we have not detected a cycle. Now DFS for cycle will again return a boolean. So we can write a check here if this dot DFS for cycle. Before we write this, the parameters that DFS for cycle will take are 3 parameters. So we have to pass the vertex. We'll pass the vertex. We'll also pass the vertex node because I'll need the vertex node to know the connections that it has. So like in vertex, I'll know that this is A that we are passing, but then in vertex node, I'll know connections are B, C, D, so on. Apart from passing the vertex, we also need to pass the parent. like we discussed in algorithm, we need the parent and we'll be switching the parent so that when we're checking for neighbors, if the neighbor is parent, we ignore that. So we just pass -1 here. Now we can check if this returns a true. So if this is true, and this is not needed since it's Boolean. So if our DFS for cycle returns a true, then we'll return a true here. We cannot directly return this. If we write return this function directly, it will fail because even in the scenarios where DFS for cycle will return a false, we'll, will be terminating the function, will not be proceeding further because we will call the return statement. So that's why only when it's returning true, that's why we have added the if condition here, then we'll return true to the caller. Okay, detect cycle. Let's go ahead and implement the DFS for cycle function, which takes vertex, the vertex node, and the parent. Okay, the checks that we have to make here are very simple. Iterate on vertex neighbors using DFS. And when we are performing DFS on any given vertex, the first thing that we'll do is we'll set the visited to true. So for vertex node, we'll set visited to true. Let me move this one level up. Now we iterate on neighbors. We'll say vertex node. Okay, it will be a for loop. Vertex node dot connections dot length. And then I can say neighbor will be vertex node dot connections index position. Okay, and if I want to know the neighbor node, these can be const. If I want to know the neighbor node, I can get it from the adjacency list using the neighbor name. Again, to simplify it, if A has B, C in its connections, then neighbor will contain the character value B and C, but neighbor node will actually have this object, which will have connections of B and C. Okay. Now we have to keep iterating on each neighbor till we see a vertex that's already visited. If it's already visited and if it's not a parent, then we know it's a cycle. So we'll say if neighbor node is not visited, then we'll call the same function. This dot, we'll check for cycle. Previously we passed vertex, vertex node and -1 as parent, but now for this neighbor, the parent will be the incoming vertex. So we'll pass neighbor. Oh, I missed the edge. Let me fix that. So I'll pass neighbor, the neighbor node. So say we are passing B and then the object of B. And the parent will be vertex here. So whichever nodes neighbors we're looking at, that will be the parent for next iteration of this. Okay, let me save this in a variable, say cycle in neighbor. And then if we have a cycle in neighbor, we return true. Okay. If there's no cycle in neighbor, don't return anything, keep iterating. On the other hand, if the neighbor is visited, if it's visited, we know it's a cycle, but we just have to make one more check. If it's visited, the neighbor should not be equal to the vertex. Sorry, should not be equal to the parent. So if the neighbor is visited and the neighbor is not parent, that means it's a cycle. So we can return true here. And I'll just add a comment. If the neighbor is already visited and not parent, cycle is found. Okay, so with this code, we'll be able to detect a cycle in a graph. let's just go ahead and create a graph object and we'll try to find the cycle. So I have some code written here, which I'll just reuse. So we have vertices A, B, and C. This is how the graph looks. And then I add one edge, say from A to B. I add one more edge, B to C, and then I can check for cycle in this graph. Okay, and we know it will return a boolean, so we can just add a if condition if we get a cycle. Otherwise, we'll just log cycle found or not found. Okay, let's execute this. So it says cycle not found. Now if I add an edge, say from A to C, so this is how the graph will look. We have A, B, C. So we have edge A to B, B to C, but then there's connection between A and C also. And it says a cycle is found. Okay, it's using the same algorithm that we just walked through and we just coded here. Let's add one more vertex to see it in action. So A is connected to B, B is connected to C. Let me remove this and say C is connected to D. And this is how it will look. In this case, will there be a cycle? We can see it, there's no cycle in it. So cycle not found. But if we connect, say, A to D, then that will result in a complete cycle. And when we run it, you can see cycle found. Or even if we connect A and C together, leave D as it is, still a cycle will be there. And when we run it, it says cycle found. Okay, if you want me to cover any other interview question, please put that in the comment section and I'll make a video out of it. I'll be uploading more learning videos to this channel, so make sure you subscribe. If you like the video, please share it with your friends and I'll see you in the next one. Peace out.